Welcome to the OLED Wave channel. Today, we're going to be reviewing a classical text-to-speech paper, which name is WaveNet, Generative Model for Raw Audio. And there are very big names on it, including lots of people we are familiar with, especially the Dr. Alex Graves is also on the paper, and Hagazin. And although the paper was published back in 2016, I would say even this 7 years passed, it is still worthwhile to read this classical paper because that represents a critical moment in the TTS research. Why do I say this is critical? Because before that, people were all resorting to the parametric approach. Before that, people even do concatenative approach. But this is the critical moment that shaped the whole paradigm. Especially, let's using this word, it shifted the paradigm from generative model to discriminative model. And also, you may ask, what are the other important moments you think that is critical to speech recognition? Because you have been working on the speech recognition for many years. I would say the recent or the latest, most recent critical moment was happened back in 2012. I think I want you to see this. It's when Dr. Jeff Hinton or Professor Jeff Hinton published this work, Deep Neural Networks for Acoustic Modeling in Speech Recognition, back in 2012, with researchers from Microsoft, including Professor Li Deng, Dr. Dong Yu, and also Jeff Hinton's student, Dao George, and other people. That's the significant change happened in speech recognition industry 10 years ago. Even this is 1 year earlier than the famous AlexNet that beats the other models in the ImageNet challenge. And if you are interested, you can go ahead and check Jeff Hinton's speech when he mentioned that he thought the critical moment that deep learning started working was the speech recognition moment. He even didn't mention about the computer vision moment happened at AlexNet, because this thing happened in 2012, which is one earlier than 2013 AlexNet. All right, let's go back to the WaveNet. And this happens 4 years after Professor Jeff Hinton introduced the DNN into the speech domain. And why? Let's see why it's working and why I call that the critical moment of the text-to-speech research. Okay. And I would say, before I do everything, I would say I would want to the traditional approach. Okay. So this is the model before WaveNet was introduced, and which is commonly used. And let's first look at the training stage. You got a speech, you send it through a vocoder analysis and text analysis, and this is a training and the acoustic model, and during synthesis you do the same thing, right? But before that, people always try to, for example, suppose let's call speech. You want to get the probability of P of X given the what do you say that? Let's say this is the linguistic feature, okay? L corresponds to this, and the X corresponds to speech. You want to estimate this, right? Traditional approach, they are always trying to decompose it into certain type of. They leverage the HMM, hidden Markov model, and they were able to convert this by using IID assumption eventually into something like this. What is S? S is certain type of hidden state, which has no physical meaning. You may say, is S a phoneme? No, it's not phoneme. It's a certain state in a phoneme. Suppose that the phoneme can represent it as a 3-state left to right hidden Markov model with the 3 states, and this happens to be in 1 state, and this is your linguistic feature, and you're trying to estimate the distribution of your speech. So you can pause the video to see what the model this is. Yes, this is generative model. It's different from the generative model we're talking about today. It's not GPT. It's exactly generative model, which means it's this. So I have to change the bigger p into lowercase p. So this probability. So this is probability given the state and the linguistic feature. There's a distribution of this, and the researchers' objective was to find this distribution. Imagine how difficult this is. So the common approach is that they use a GMM with mixtures. They call it to try to make their estimation of the distribution as close to the X as possible, right? But think about it nowadays, what people do, okay? Let's say speech recognition or other applications. People are always using discriminative model. Discriminative model means that suppose you are still required to estimate this. You can even you can reduce the X to certain things like this. But there's no hidden state. I shouldn't write this. But the point is, in the descriptive model, what you should do is when you are asked to estimate this, you do not try to estimate the probability distribution or the probability density function of X. You just compare the X. So suppose this is your estimated X, and with the ground truth X, okay, and you compute a loss function. Say the loss function function between these two, right? Then what you do is trying to minimize the value of your loss. So in the end, when your loss gets smaller and smaller, that means your probability estimation gets closer and closer to the P of X given H. And in this way, you do not have to estimate the probability distribution anymore. I think I've explained many times in the video why it's difficult to estimate this probability distribution. It's generally because it's a dilemma, because during training, you would always have unseen cases, and it's prohibited you from estimating the exact PDF of px given something, right? And also, this is not end-to-end. And this is end-to-end. Discriminative model, nowadays, people can make it end-to-end. That makes less human intervention in the model training as possible. So it leaves the modeling, the modeling task to the computer or the AI, other than leveraging expertise or human experience into the modeling procedure. And that varies a lot according to person, right? And especially when you play with discriminative model, you can leverage a great amount of data and stochastic gradient stuff. While in generative model, in the generative model, you cannot use stochastic gradient descent method. You can only use GD, gradient descent method. You cannot use a mini batch or something like this. So you cannot leverage the fantastic deep learning techniques. So this is why the generative model is becoming less and less. I think nowadays nobody uses that. It's becoming obsolete. But before 2016, people are all using the generative model. And this is when 2016 comes to 2016, these people introduced this descriptive model into the TTS domain, speech synthesis domain. And the result was was fantastic, I would say. I still remember that 7 years ago. Actually, this paper was released early in 2016, I think. So maybe 7.5 years ago. When I heard the audio samples, I was shocked, and I never heard that high quality text to speech synthesized the results before. But you say, wait, how about concatenative speech synthesis? Well, that's another story. But the concatenative speech synthesis, you cannot synthesize word or phrases other than in the concatenated units, right? It's natural, but it's not that flexible as people do in the parametric based TTS. Okay, so let's look at the algorithm. And I also want to say something generally about the algorithm. So when I think nowadays there are many tutorials, tech writings about the papers on internet. My recommendation is that unless this is written by the author himself, you should always read the paper first. And then, if you are still couldn't understand the paper, you can resort to third-party information, like my OLED Wave channel. You can try to watch the video to see if I have covered any issue that you cannot understand. But try to read the paper, and especially this classical paper, which was published 7 years ago, because the algorithm part is very straightforward for you to understand. First, the paper talk about the RNN, recursive neural network, right? So you can see they convert the issue of estimating the probability of a certain waveform. The waveform is from 1 to t, and at each time point, the x value could have 563 samples, which is 2 to the 16 values. And you can imagine that suppose the time is, and suppose every second you have 22,000 samples, which is the sampling rate 50. And suppose you have an audio of 5 seconds, And so imagine how big the feature space or the possible values that the X could have. This corresponds to 16-bit DCM. Okay, so this is a huge number of amounts of feature space. I think this is way larger than most high resolution image right now. So this is why I personally think that speech synthesis is way difficult than image generation, because the feature space or the eventual generated audio has a way much bigger space than the image. So you can imagine that. Remember, I make an analogy here. Remember, people, Deep Blue, IBM's Deep Blue, they beat Kasparov on chess. I think that was back in 1994. But it is only till recently, after 2000, I think 2000, the first decade of 2000, right? The second decade of 2000, that the Deepmind, also the institution of this paper, they invented AlphaGo to beat the Lycidon in Go game. Why? Because the search space, the strategy search space of chess or the Go, the search space of the strategy search space of the Go is way much bigger than the search space of chess. So think about how many points the player can choose on the plate, right? Compared to chess. Chess only is 8 by 8, but Go is 19 by 19. So the way bigger space. I think this is why even this today is 2023. The text to speech quality. Let's talk about the AIGC domain. Okay, AIGC including the text, video, and audio, right? Or speech is one subdomain of audio, but the text is doing fairly good, GPT, and the video, I think, is behind GPT in my personal opinion, but it's generated very well. But if you look at audio generation, if it's a MIDI music or piano music, okay, it's okay, it's good. But if you are coming to speech, I personally say it's not there yet. I think the reason is simply because the search space is too big. Okay, let's go back to the paper. By using the conditional probability or IID assumption, they can break down this probability into this one. So that reduces the computational cost. And you can see that this probability can be easily modeled by any recursive neural network architecture, correct? And this is why the authors, they come up with this, something they called dilated causal convolution. Let's call it DC conv. Okay. And this doesn't come from nowhere. It's also the first author of this paper. Also this year, the author come up with something called a pixel-CNN. Okay. I think 7 years ago I did read this paper, but I cannot recall the details of it. But if you do need me to read this paper, I can read it for you. It's also a classical paper. But the difference of the pixel-CNN versus the dilated causal convolution mentioned here, I guess it was because in this paper, this dilated causal convolutions, although the author didn't mention anything called recursive, but actually this is a RCN. What do I mean? It's recursive convol network, or say it's a recursive DC, or this is a recursive DC convolutional network. That makes sense. They also omitted the word recursive because of why? Let's see the first case, the case without dilation. It's just a causal convolution. So basically, you have, suppose this is all your speech input. This is each speech sample. Each sample can have 2 to the 16 values, 2 to the 16 values. But you can definitely have a convolutional network with a receptive field of 2. I should draw this, right? Then after the convolutional network, you got a sample here. I can do the same thing with other inputs around here. Then you got something here. Then you keep doing this, right? You can keep doing the convolutional network. Then you reach to the upper until you get the output. And you can see why it's called a causal. Because the receptive field of a convolutional network never look at the future. There's no future. Or it's not allowed to look at future. You can only look at the current sample and the past sample. This is why it's causal, right? I guess this is fairly easy to understand. Although they say you can see the receptive field is 2 and they have 4 layers. So the final receptive field of the network is 4 plus 2 minus 1, which is equal to 5. But you can also regard the space between these two as a receptive field, not just a 1, but a 1L. Let's call that 1L. L can be any value, okay? L can be, suppose L equals to 4, okay? Then you have to draw these another 2 extra arc here. They come up with L is equal to 4, okay? But it's trivial. What I meant is that the receptive field of first layer doesn't necessarily have to be 2. They also only demonstrate this. They're saying that there's a reduced, or that they keep the dilation value to be 1. So every so how to say this? Because this is causal, right? So the receptive field is linearly grow with the, what do you say that? The number of layers, not linearly. It's a, suppose that the layer size is X. The receptive field is only like X plus A. It's not linear. It's just what do you call this? X plus A. Oh, it's a shifting. It's just a shifted off version of the number of layers. The receptive field. Receptive. I think speech people mainly call this the window size of the network. But computer vision people like to call it receptive field because it's related to the vision. Okay, this is the number of the layer. And then it's time to move on to the dilated part. Why is dilated? Then we can see the next figure that the author is trying to show you. This is the same, right? Let's see, look at these two. This is the same. And we reach to this. But when but this time it's different, right? It no longer take these two as input for the next layer. No. Instead, it use a dilation of 1. So it skipped one, skipped one past sample. And they use this window to get this, right? And when they go to upper layer, they change the dilation to be 2 times of the dilation on the lower layer. So they move on, they got something like this instead of getting this, right? No, they're not getting this. So they're not getting this anymore, right? Instead, they're getting this receptive field. So 2 times of the, it's, I wouldn't say 2 times. It's grows 2 times with a shift, okay? And then eventually onto this one, it has this receptive field grows another 2 times with a shift. So why they do this? Oh, I forgot one thing. This is still causal. You see, never look at the future. Okay, remember that. So why they do this? They also they mentioned they have 2 folds. They increase this. They can increase the receptive field, because for speech, not only speech recognition but also for speech synthesis, having a big receptive field or a big context window is important. Suppose you do this, and your context window is like it cannot grow exponentially with the number of layers. So you can see this layers is like 4 layers, right? And the receptive field is growing exponentially with a bias. Grows very fast, especially when your model gets deeper and deeper. That means, like they mentioned, that they stack blocks of these DC convolutional blocks together. You see this? That means they can get even bigger receptive field. And then eventually they end up with a convolutional field of, I think they say something in the paper, they call it 240 milliseconds or about 300 milliseconds. And say the sampling rate is 2050 hertz. Let me remove this. That means let's do an approximation, okay? Okay, eventually they have a receptive field of about 5,000 samples. And this is way more efficient if you're just having a counterpart, for example, 1 times 5,000 convolutions. Because in this network, you can see lots of the connections are empty, right? You see, this is this is why I call dilated, or lots of weight is 0 compared to a CNN with a receptive field of 5,000, correct? Which means the model can train more efficiently, can go deeper with the same model size. Sense? I think the rest are very easy to understand. Softmax distribution, they apply the mu law, very, very trivial, to reduce the change the dynamic range of the output waveform. And this is something I want to mention, a gated activation unit. Why they're using this here? The reason was because although this is recursive CNN, but there's no gating mechanism like people do in the LSTM. Remember, in the LSTM, you have an input gate and a forget gate. Or those 2 gates controls how the long-term memory flow through or across time, okay? in order to have this type of long-term memory controllable, they introduce the gated activation unit, and this is the filter, and this is the gate. Okay. And then eventually, they come up with this architecture. I think it's very interesting to understand. This is residual, and for different layers, they add this skip connections. So, for example, suppose there are 10 layers. Even the second layer can have a direct connection to the eventual output, or almost eventual output, right? You see the connection here is submit over here. So this is called a skip connection. What is the benefit of skip connection? Is that I think it allows the gradient to flow through more easily. There's less amount of gradient vanishing issue if your model gets too deep. And this is especially good when you want to fine tune your model. Remember, this is like a weight matrix, right? So when you have, no, sorry, there should be a weight matrix somewhere here. I think they didn't draw this. Or suppose there's a weight matrix, okay? So when you want to fine tune, if there are skip connections, you can just play around, or play around the weights out here, other than tweak everything the models here. If you do not have enough amount data, you don't have to change the weights in the matrix weight in these blocks. You only have to play with the skip connection weights, and it still works if you do not have enough amount of data. It's good for fine tune. Okay. So why they call conditional WaveNet? Right. The speech synthesis, the input is a linguistic feature, or the fundamental frequency. It has two things. So you cannot just start from a wave sample of 0 and start to recursively generate things. You cannot generate out from nothing, right? So this is why during the generation, you do have to have a linguistic condition over here. So that's easy to understand. And this also comes to the filter of the gated activation unit, and the gate of the gated activation unit, which is easy to understand. This is a trivial. Let's go to the experiment. They tried the multi-speaker speech generation. You can click the link and listen by yourself. It was amazing 7 years ago, and I would say they are still good nowadays. Text to speech, and the result was this is very surprising. You see, if you play with the natural speech, you're gonna get a 4.4 MOS score, but they are reaching 4.2, which is a big leap over the concatenative based approach, which should be better than the parametric based approach. And this one, I think, is, although they're doing the LSTM-RNN, it's only, I think, it's controlling the linguistic feature things. I don't think it's a discriminative model. It's still generative model. Oh, I might be wrong. This might be already some descriptive model, but I'm not sure. I haven't looked at this baseline. For this result comparison, they first compare the concatenative based approach and the LSTM based approach. The LSTM is not WaveNet, it's some baseline. And you can see that for English, concatenative is preferred. But for Mandarin Chinese, I don't know why the LSTM is more preferred. Maybe the concatenative one is not doing well. This is counter my intuitive, because even for Chinese speech synthesis, concatenative is always preferred compared to the LSM based approach. But no problem. Then they compare, let's say, the third figure. So this is called the best baseline, because they have two alternative baselines, and you can see the WaveNet L plus F is always preferred for English and Mandarin Chinese. But sometimes for Chinese, it's more vague, because you see lots of people do not prefer certain this or that. For WaveNet, the WaveNet linguistic feature, or linguistic feature plus F0, F0 means human pitch. Seems that this is better, right? See, this is preferred, this is preferred. Easy to understand. Yeah, this is not why nowadays people always add the pitch value control in it. All right. else? I think I will stop here. I would say it's always feeling good to read or rewind back to read those classical papers. It gives us a privilege to see what people are thinking at the very beginning and how that evolved to something we have today. All right. Thanks for coming to our channel. If you have any comments, please do. If you like our channel, please subscribe. And if you want to share with your friend, feel free to do so.